So this video is just going to shore up the very last page of notes in section 2.1. And this is just getting us ready to think about the harmonic oscillator problems that we're going to be running into for quite a bit of the rest of the course. So first of all, we're going to be looking at something called an undamped harmonic oscillator. And so the word undamped is really just a fancy way of saying there's no friction. And a harmonic, anything that's harmonic in nature, tends to be periodic. This is just an old-fashioned way of saying periodic. And an oscillator, well, you probably know what an oscillator is. It's something that moves. There's motion. There's back and forth motion. So an undamped harmonic oscillator is something that's moving back and forth in a periodic fashion with no friction. Now, you probably realize that saying no friction makes it kind of impossible, but for our purposes, it's the beginning of understanding what's going on. So what do we mean for a harmonic oscillator? In our case, we're going to use a pretty simple harmonic oscillator. It's going to be just a spring that's attached to a wall, some fixed location, and it's also, the other side is going to be attached to some mass. So we've got some mass M, and we have some spring attached to it, and we're basically going to call its position, we're going to use the variable y. And so this is its initial position. Call it 0, where the spring is just sitting there and nothing's happening. And if we take the mass and we move it to the left, we're going to kind of scrunch up the spring and it'll push back. It'll make it want to go that way. And if there's no friction between the mass and the table here, I just said it's a table, we'll just make it a table, then that means the mass would just kind of wobble back and forth and back and forth. And so when we compress the spring, we say we're going to move in the negative y direction, and when we stretch the spring, stretch the mass out this way, that'll be in the positive y direction. That's just kind of setting up our frame of reference here. And so if you've had even just a little bit of physics or physical science, you probably know there's a relationship for what goes on with the spring, but there's also a relationship of what goes on with any mass, and we call that relationship Newton's second law. And so notice I say recall, like I expect that you've seen this at some point in your careers here. But Newton's second law says that the net force on an object is equal to that object's mass times whatever acceleration it's undergoing. So if it's not speeding up or slowing down or changing direction, then this thing has no acceleration. And just as a reminder, the acceleration really is the first derivative with respect to time of velocity. And that's the velocity is the first derivative of position. So this is also, acceleration is also the second derivative with respect to time of position. In our case, we'd use y. Position is y. And so velocity is the first derivative with respect to time of position. So just kind of basics. Newton's law says that the net force on an object is equal to its mass times whatever acceleration it's experiencing. The other thing that we have to know in order to kind of set up our differential equation here is we need to know something called Hooke's law. And this is named after a fellow by the name of Hooke, go figure. But he actually wasn't the person to discover it. Hooke is pretty famous in scientific circles. He and Newton were about of the same era. And Hooke is famous for stealing other people's ideas. And he actually stole somebody's idea and wound up, it became Hooke's law, but it really wasn't his idea. And what he says is that there's a restorative force. And the force that restores the mass to its position. So if I move it this way, the force is going to push to try to restore it to its position. If I stretch the mass this way, it's going to try to pull it back to restore it to its position. And the restorative force is equal to some spring constant k times position y. And so this guy right here, that's the spring constant. And because it's restorative, this is always going to be kind of opposite whatever direction you're moving. So if I stretch the spring this way, then the restorative force is in the negative direction. And if I squish the spring this way, then the restorative force is in the positive direction. So Hooke's law says that you've got some spring constant, and that's literally how much stretch per unit force, right? So it's basically saying how far does it stretch per unit force. And so putting these two things together, we can wind up with another really important concept, and that's if you take your net force on the mass, that's got to be equal to the only force that's on the mass is the restorative force, because there's no friction. So there's nothing else going on other than the restorative force. So if I grab this thing and I move it out here and then I let go, it's going to feel a force in this direction because the restorative force is yanking on it. And so what that means is our net force, which we know is mass times acceleration, is going to be equal to our restorative force, which we know from up here is negative k times y. And so what we have is the beginning of a really interesting equation, because that, of course, that acceleration is the second derivative of y. So writing it more plainly, we can say mass times the second derivative of y with respect to t is equal to negative k times y. Scoot that up a little bit. And what we've just found is we have a second order differential equation. And that differential equation models our spring, our simple harmonic oscillator, right? Simple because there's no damping, harmonic oscillator because it's just a mass moving back and forth. So off to the side, we're going to make note of the fact that m and k are parameters. And that means they're actually numerical values that we can set to be whatever we want. So we can make that mass as big as we want, and we can make that spring as stretchy as we want. So right here, if we stopped right here, we have a second order differential equation that models our mass and our spring. But there's a way that we can rewrite this. So if you remember, we also know that the second derivative of position with respect to time is the same thing as the derivative with respect to time of the velocity. And on this side we have k times y. And the other thing that we know is velocity itself is equal to the first derivative of position. So what we have now is the beginnings of a system of first order differential equations. So I'm going to rewrite this in a slightly different way, and hopefully you'll be able to see how they become a system. What started off as a second order differential equation becomes a system of first order differential equations. So I'm going to manipulate this one a little bit and write it as dv dt equals, I'm going to divide both sides by m. I get negative k over m times y. And the other equation, well, the other equation was kind of already set up for us, which is dy dt equals v. Now I kind of dropped the notation of this being a function, as we've done before, and now what we have is these two equations taken together are a system of first order differential equations. And this system also models our simple harmonic oscillator. So whether we are talking about a second order differential equation all in one piece or two first order differential equations, and in this case the first order differential equations have dependent variables that are y of t and v of t. Up here, the only dependent variable was y, right? Because it was the second derivative of y and y on the other side of the equation. So it turns out that the second order differential equation and the first order system are equivalent. And this is good for us because we may not know how to solve this second order differential equation, but we know how to manipulate, we know how to produce a graph, a DE plot, and we can understand what's going on with this first order system. And so you might ask, okay, that's great, but I really want to solve this thing. Well, we can ask the question, what does a solution look like for this system? And so what we're going to do is we're going to go into Maple and say, hey, dy dt equals v, and dv dt equals negative k over m times y. This system right here, we can actually throw that in Maple to see what happens. And just for giggles, to keep things simple, we're going to let k be the same thing as m in terms of magnitude. So they're not the same thing in terms of units, but k and m, if they were the exact same size, this thing would simplify down to k and m. So what I'm going to do is I'm going to actually make this in the Maple notes. And so you can check this out in Maple, the Maple notes. And you'll be able to see what happens when we take a look at a DE plot for this, what happens when we just try to desolve this. And you'll find out it's actually kind of interesting. It's not the kind of solution you'd expect just looking at them. So that's it for now. That gets us to the end of section 2.1.